Hello. Last time, I organized the big picture by comparing computer to a kitchen. Let me organize again. So, the CPU is a shop who actually cooks. RAM is a countertop so that the shop can reach immediately. Storage, the fridge, or storage room. And the operating system is a kitchen manager who organizes the whole workflow. But there's still one real important question left. When you click a browser icon once, what exactly happens inside the kitchen? This is what I'm gonna talk about today. Let me say that I run a program. Behind the sentence, the operating system actually manages a lot more than it seems. And today, I want to organize the whole process using the same kitchen analogy. First of all, a program is a bundle of instructions, but it's not working yet. It's just stored. In other words, it's a file sitting inside an SSD or HDD. And the kitchen analogy is closer to a recipe and ingredient set. So it's still sitting in the fridge. Nothing is on the countertop. Nothing is on the pan yet. The fire's not on. And everything's just sleeping. But when the operating system puts a program into RAM and makes it executable, it becomes a process. In other words, a process is a program that is currently learning. And the kitchen analogy, that's the moment when the ingredient is taken out of the fridge and onto the countertop, so the actual cooking begins. When a process is loaded into memory, it can be divided into four areas as code, data, heap, and stack. The code is literally the area that contains the instructions to execute, and the kitchen analogy is kind of recipe for cooking. The data is an area that stores global and static variables. These variables stay in memory for the entire execution of the program. Here, static does not mean that the value never changes. It means that the variable casts memory space while the program is loading. There's something different between static variables and global variables. The global variable is able to be accessed by other files, but static variables not. The heap is dynamic area. It depends on how much space is necessary. When the order is for just one portion, I don't have to get the most space. And the stack is working memory related to function calls. Things like local variables, parameters, and return addresses are stored there. In the kitchen analogy, it's kind of recording how far the cooking stops. Then, what is a thread? It's quite confusing. A thread is the actual flow of execution inside a process. Let me talk about making fried rice. Customer places an order, one fried rice. I can say that one order fried rice is a kind of process. When I make a fried rice, I muscle a lot of eggs, prepare the rice, stir-fry the meat and vegetables, and then adjust the seasoning at the end. So thread is an individual workflow that's running concurrently or in parallel. The important point is that a thread inside the same process shares the same address space. In simple terms, they're using the same order sheets, the same ingredient storage, and the same shared source containers together. So each thread still has its own current execution points, its own register values, and its own stick. But each thread doesn't have any its own separate address space. It shares the process memory with the other thread. That's why the thread is lighter than process. And now, I will talk about process states. A process is not always learning. The operating system usually manages processes by dividing them into states, such as ready, learning, and waiting or blocked. Learning means that the process is actually holding the CPU right now and executing instructions. In the kitchen analogy, that's when the chef is standing at the pan and actually cooking the dish. Ready means that everything is prepared and the process is ready to learn. but it's still waiting for turning into a CPU. In the kitchen in the lodge, the ingredients are already out and the cooking order is already planned. But the stove is still occupied, so it's waiting in line. Waiting unblocked means that even if you gave it the CPU right now, it still could not move forward immediately. For example, it might be waiting for more data from the disk, waiting for a network response, or waiting for keyboard input. And now I want to talk about something important. There's one CPU core. Only one execution flow can actually run at a single moment. So then how is it possible that the browser is open, the music is playing, messenger notifications are coming in, and the file is downloading at the same time? This is where the idea about CPU time becomes really important. The operating system divides CPU time into really small pieces and distributes them among execution flows such as threads. For example, it may learn A for a few milliseconds and B for a few milliseconds and C, and so on. This switching happens so quickly that it seems to be learning at the same time. It's not totally simultaneous, but just extremely fast and taking. Actually, there's some kind of system in parallel. But the basic principle of the multitasking is the time-sharing mechanism. When the operating system switches from one task to another, current process must remember its own current state for the future. That's why context switching is necessary. Then, what is context switching? And what does context mean in the OS? Context means the information of the currently loading task. It's like some program counter, register value, and stack pointer. Then it restores the same kind of information for the next. When a timer interval occurs, the hardware and operating system work together to save the current states, load the next states, and continue execution. Switching between threads is similar, but threads inside the same process share the same address space. So like switching between processes, there's no need to replace the entire address space. The important thing is that there's a switching register values and stack context for each thread. And now, let's move on to the problem of deciding which task should be placed on the CPU first. It's gotta be handled by the operating system. So I can say that's CPU scheduling. The simplest one is FCFS, first come, first served. It works in the order they arrive. Let me take some restaurant analogy. The customer who orders first should be first handled, but if one very long task got stuck at the front, then all the short tasks behind it get blocked for a long time. Therefore, in addition to this simple one, there are many kinds of methods to solve several issues. So then there is a SJF, shortest job first. This means that the system handled the shortest job first. In the kitchen analogy, it's like serving an espresso, a Coke, or a simple side dish first, because those are able to be finished quickly. It's quite powerful for reducing average waiting time and completion time. But in reality, long jobs may keep getting delayed. So there's a way to solve this issue. It's a SLTF, shortest remaining time first. If a newly arrived job has a shorter remaining time than the one currently learning, the operating system preempts the current one and finishes the shorter one first. Average performance can be improved, but switching happens more often, and long jobs may end up waiting for a long time. It's unfair. Then there's a famous algorithm. It's a round robin. Round robin makes a lot of slices with dividing every task. I can say that it makes a lot of time quantums. So every slice has the same time. It should be fixed, and it's running in rotation. In the kitchen knowledge, it's like giving pasta 5 minutes, salad 5 minutes, steak 5 minutes, and going along the loop. Because of that, responsiveness is good. It fits system with a lot of user interaction. But if quantum is too short, the system spends more time switching than actually doing work, then the overhead is gonna be large. If the quantum is too long, then it becomes similar to FCFS, first come, first serve. Priority scheduling means that the system should handle higher priority tasks first. You can think of it as taking care of urgent orders. The lower priority tasks kept getting delayed. We can say that it's a starvation. So there's a one way to reduce it. It's an aging. It gradually increases the priority of tasks that have been waiting for a long time. Multi-level queue means separating tasks into completely different queues based on their type. For example, interactive jobs might go into one queue and batch jobs into another, and each queue can use a different scheduling policy. The problem is that once a task is placed into one queue, it may not move easily, so lower queues can still be treated unfairly. That's why a smarter version was developed. It's a MRF queue, multi-level feedback queue. This one lets tasks move up and down between queues depending on how they actually use the CPU. Short tasks can stay near the top and get started quickly, and some tasks that hold the CPU for a long time can be pushed back to preserve overall responsiveness. Now, let's compare the two scheduling styles, preemptive and non-preemptive. Non-preemptive scheduling means like this. Once a task gets the CPU, it keeps using it until it finishes. The operating system does not stop in the middle. It's simple, but it can be slow. If one task takes too long, other tasks are gonna wait. Preemptive scheduling is different. The operating system can stop a running task and give the CPU to another task, so even if the one is slow, the system can still respond. That's why modern operating systems usually use preemptive scheduling. So in short, non-preemptive means the CPU is not taken away. Preemptive means the CPU can be taken away. Let me summarize so far. Our program is a bundle of instructions stored on the storage, and a process is that program in the middle of actual execution. A thread is a flow of execution that actually moves inside a process. Data from memory structures, cut data, heap and stack, and data for process states is ready, learning, and reading. And during the process, it uses context switching to save the state of the previous task and restore the state of the next one. In the end, the operating system is really similar to a manager who's running a kitchen. It decides who gets to use the stove now, who has to wait, and which order should go out first, so that everything stays organized. So today, I wanted to explain how the process is managed. If I got something wrong, please feel free to let me know in the comments, and I really appreciate you watching this video until the end. Thank you. Bye bye.